Hi guys, welcome back to Calculus with Mr. Robeson. Today we are going to discuss what are discontinuities, and we're going to go over the actual definition for continuous. So not just the you can draw it without lifting your pencil kind of thing, what it actually means in terms of limits. All right, so here we go. 3 conditions are needed for a function to be continuous at a point. And if it's continuous at that point, at every point in the interval, then it's continuous on an interval. All right. If it fails to be continuous, then we say it's discontinuous. All right, so the 3 conditions are, number 1, f of c is defined. So we have no holes, so we don't have a hole. And we have no vertical asymptotes at those, because those two will cancel out being continuous if there's a hole or a vertical asymptote. Next, the limit exists. All right, well, if the limit exists, that means we don't have a jump. All right, both sides would have to go to the same value for the limit to exist. And then we need, I guess we could have an open hole. That wouldn't work, but if the hole was filled in, that would be okay. But if we have now that the limit exists and that limit equals the function value, then it is continuous. All right, we do have to check all 3 on the AP exam. So all 3 of these you'd have to go through. So like if you're doing a problem, you'd have to say, okay, the function value is equal to this. The limit value is equal to this, and those two are equal to each other, so then it's continuous. So you have to do all 3 on an AP exam. Also, if you're told it's continuous, then you can work backwards and say, okay, if I've got the limit, then it's going to be the function value, or if I've got the function value, that's going to be the limit. All right? So it's very useful to go back and forth. Right? And we usually talk about continuous on an open interval, so we usually don't include endpoints. So we're not using brackets, we're using parentheses here. If it's continuous everywhere, we say it's continuous from negative infinity to positive infinity. All right, so here's our 3 cases where it's not continuous. So here's our hole. All right, even if we had another point here, like say there, it still wouldn't be continuous because the function value does not match the limit value. The limit value would be up here. The function value would be down here. Not continuous. Here's our jump. All right. Here the problem is the limit does not exist. All right. So since the limit does not exist, it can't equal the function value. The function value is up here. So the function value does exist. The limit does not exist. So that doesn't work. Oh, here's our other dot. So here's the hole with the dot. And there we go. That's also not continuous. All right. So these two kinds of discontinuities, we have ones that are called removable discontinuities. This is our hole. All right. So if we can fill in our hole, that's called a removable discontinuity. We just change the function value to fill in wherever that hole is missing. Non-removables are our jumps and vertical asymptotes. All right, so those guys have special names. So there's our 2 examples of holes. And there's our jump and our vertical asymptote. All right, so let's take a look at these functions and see if we can just classify their discontinuities. So with this one, f of x equals 1 over x, we could graph it if we want. Just throw it in your calculator. Hopefully you know what that graph looks like. All right, it looks something like that. And like that. Make sure to put arrows on the end of your graphs. And it has a vertical asymptote at x equals 0. Right? When this bottom equals 0, it has a vertical asymptote. So this is where it's discontinuous. So this is a non-removable discontinuity. All right, if we take a look at the next one here, so we could type this in our calculator. If we did, we'd have to put parentheses around the top, parentheses around the bottom, and type it in. All right, we could also see if we could simplify this first. All right, the top of this guy factors. It's a difference of squares. That factors into x minus 1 times x plus 1 all over x minus 1. So the discontinuity right here is that x can't equal 1. We can't have 0 on the bottom, but that cancels out with the x minus 1 factor on top. So that must have been a hole. So we call that a removable discontinuity. All right, we just removed it by canceling it out. I mean, technically it's still going to be a hole, but if we could fill in that whole value with just using the function x plus 1 as our graph, that would fill in the hole. That would be a removable discontinuity. All right, next we've got a piecewise function. All right, we say it's piecewise because it has one piece when x is less than or equal to 0, and another piece when x is greater than 0. All right, x plus 1 is a line, so it's always continuous. X squared plus 1 is just a parabola, so it's always continuous. So the only place where it could be discontinuous is where it switches functions. So at 0. So we're going to check 0 in each one. So if we plug in 0 to the top guy, we've got 0 plus 1 equals 0. If we plug in 0 to the bottom guy, we've got 0 squared plus 1. Oops, not equals 0, sorry. Equals 1, equals 1. So from both sides, it goes to 1. The function value is also 1. So we've got that h of 0 equals 1. And we've got that the limit as x goes to 0 from both sides in h of x is also 1. So the function value exists, the limit exists, and they are equal. All right, so this is continuous. All right, everywhere. So we could say from negative infinity all the way to infinity. All right, and our last guy here, sine of x. So we've looked at the graph of sine of x a couple times already. Hopefully you remember it starts at 0 and goes up, and then down, and then up, and then down. And if we go backwards, we just keep doing the pattern, but backwards. It keeps going forever. It's nice and smooth. The function value is defined everywhere. The limit is defined everywhere. So this guy is also continuous everywhere. So from negative infinity to infinity. All right, so here is a practice question. Discuss the continuity of f of x equals x minus 3 over x squared minus 9. So figure out where that is continuous and where it's discontinuous. If you need to, pause the video. Thought I erased that, but okay. All right, so let's check it out. Let's see how we would go about doing this. So we would want to take this guy here and say, okay, well, whenever the bottom equals 0, that's going to be a discontinuity. So if we set the bottom equal to 0, well, we would factor that into x minus 3 times x plus 3. So we get x equals 3 and x equals negative 3. All right, so technically we want to say it cannot equal 0. So x cannot equal those two. So those are our discontinuities, both of those. So now we want to discuss each one. So what's happening at each one of these guys? Well, if we look on the top, we've got an x minus 3, and on the bottom, when we factor it, we've got an x minus 3. So those two are going to cancel. That means this guy is a hole. He's removable. All right. This guy did not cancel. It's a 0 on the bottom. That means he is a vertical asymptote. So we want to have a vertical asymptote at negative 3. And we want to have a hole at 3. Those are our discontinuities. If we were going to write it out in interval notation, this would be from negative infinity to negative 3. Then we start back on the other side, negative 3 to 3. We can't include 3 because there's a hole there. And then from 3 to infinity is how we would write out that interval. All right, so that's interval notation. If you want, you can put the little union signs between them to say this or that. All right, so our answer there is D. All right, so that was a quick little look at discontinuities and what it meant to be continuous. So remember, you've got your 3 conditions to be continuous. F of c exists. The limit as x goes to c of f of x exists. And then those two things are equal to each other. So the limit as x goes to c of f of x equals f of c. That's how we check continuity. That's it for this one. All right, next video we'll take a look at some more types of fun limits. Bye.